So, welcome to module 33 of this course. In this module, first we will broadly discuss about the statistical inference problems, and then in particular we will discuss about the point estimation problems. So, we have the following setup. So, the basic situation in statistical inference problems is as follows. So, what we have is we have a population and we are interested in certain characteristics of this population. So, we seek information about characteristics of a collection of elements called population. Now, when we need information about characteristics of this population, the best thing would be to take observations on each and every element of the population and then make certain inferences. However, due to various reasons such as time, cost and other factors, we may not wish or be able to study each individual element of the population. It may be too expensive, it may not be practically possible to examine each and every element of the population. So, what we do is, our object is to draw conclusions about the unknown population characteristics on the basis of our information on a characteristics of a suitably selected sample from the population. So, what we do is we just take observations on a part of a population, which we call as a sample, and this sample has to be suitably chosen. And based on this sample, we try to make inferences about the unknown characteristics of the population. So, formally, let the random variable x, which may be vector valued, describes the characteristics of the population under investigation, and let f be the distribution function of x. So, if I have a population whose characteristics x have a distribution function f. So, first let us consider the parametric statistical inference problems. Here the random variable has a distribution function f which is indexed by an unknown parameter theta. But in this case what we know is functional form of f theta is known. The only thing which is unknown is this parameter theta. So, except for the unknown parameter theta, I know everything about the distribution of this population. So, let theta be the set of possible values of the unknown parameter theta. So, in problems of parametric statistical inference, the statistician's job is to decide on the basis of a suitably selected sample, generally a random sample from f theta, which member or members of the family f theta can represent the distribution function of x. So, we have already assumed that the population has a given functional form, distribution function or the PDF has a given functional form. But that given functional form has certain unknown parameters. Now, these unknown parameters, if are known, then you know everything about this population. But these unknown parameters we do not know, and the goal is to how to estimate these parameters. Because if I can get an estimate of these parameters, I can get the estimate of the probability density function or the probability mass function. So, the goal is to estimate this theta, which is unknown. What happens in non-parametric statistical inference is, even the functional form of f is unknown, and I have to make inferences about the whole distribution function f based on the random sample. What we may know at the most is possibly that f is absolutely continuous or f is discrete. Apart from that, we do not have any information about f under non-parametric statistical inference problems. So, the statistical inference problems are broadly classified into two groups: the parametric statistical inference problems, where I know the functional form of the distribution. The only thing which is unknown is the unknown parameter associated there. In non-parametric statistical inference problems, we do not know even the functional form of the f, and we have to make inferences about f. In particular, I may be interested in estimating what the probability distribution is or what the distribution function f is. So, I need certain information about the population. So, in statistical inference problems, the statistician can observe an independent observations on x. The random variable describes the population. So, this gives us the information about the population. Or in other words, the statistician can observe n values x1, x2, xn assumed by the random variable x. So this would be in form of a sample. Each xi can be regarded as the value assumed by a random variable capital Xi, because once you are taking observation from the population, that observation is random depending on which observation has been chosen. So in a sense, it is an observed value of a random variable xi, capital Xi. The observed values x1, x2, xn, which you do after experimentation, are then the values assumed by the random vectors x1, x2, xn. Now the set x1, x2, xn is then a random sample of size n taken from the population having distribution function f. So I have that means a random sample from the given population. Now the observed values of the random sample are called the realization of the random sample. So after I have conducted the experiment, I know what are the observed values. So their values are, those values have been observed values of the random variable, and those we call as realization of the values of the random variable. So let us look at this definition. So the space of the possible values of the random sample x1, x2, xn is called the sample space. We will denote the sample space by chi. Generally the sample space chi is either the support of random vector x, or it could be interior of the support in the case of absolutely continuous random variables. So in the parametric statistical inference problems, the set theta of possible values of the unknown parameter theta is called the parameter space. Because in parametric statistical inference problems, I know the functional form of f. The only thing I don't know is the value theta, that which could be vector valued. What I know is theta takes values in this set, which is capital theta. So the set of all possible values of the unknown parameter theta is called the parameter space. Let us consider this example, which is an example of a parametric statistical inference problem. So suppose you have a manager who wants to make inferences about the mean lifetime of a bulb, of a brand of an electric bulb manufactured by a certain company. So there is a certain company which manufactures bulb using a given manufacturing process, and I'm interested in knowing what would be the mean lifetime of the bulbs produced by this company. Here the population under investigation consists of lifetimes of all the electric bulbs produced by that company. So that is the whole population. Suppose that the random variable x represents the lifetime of a typical electric bulb manufactured by the company, because different electric bulbs produced by the company would have different lifetimes. So there is some amount of randomness which is there in terms of the actual lifetimes. And I assume that that randomness is captured by this random variable x. So in other words, the random variable x describes the given population, which is the lifetimes of all the electric bulbs produced by the company. Now probability modeling on the past experience with testing of similar electric bulbs indicates that x has an exponential distribution with mean theta. So basically when I assume that it has exponential distribution, I am assuming that it has no aging property or memoryless property. Or in other words, the electric bulbs do not age with time. That is, in terms of electric bulb, is a valid assumption. Because electric bulbs normally fail only due to voltage fluctuations. So if there is an ideal situation where voltage is perfect, the electric bulbs will not fail. Because that filament is under vacuum which never fails. It fails only because of certain voltage fluctuations. So if there is perfect condition, the assumption that the lifetime would be represented by exponential distribution is a valid assumption. So that means my distribution function is of the following functional form. So that is why it falls under the umbrella of parametric statistical inference, because I know the functional form. What I don't know is this theta. So but the value of theta is not evident from the past experience, and the manager wants to make inferences about the unknown parameter theta. Now in the case of exponential distribution, I know this theta is same as the mean of the population. So that is the mean lifetime of the population. So expected value of x, we know for such an exponential distribution is theta. So, what are the possible values of theta? Theta is 0 to infinity, it could be take any value from 0 to infinity. Now, due to various considerations which I explained before, like time, cost, etc., the statistician cannot obtain the lifetimes of all the bulbs produced by the company. It would be too expensive. Even if you do it for a year, it may be too expensive. So, one way to obtain information about unknown theta is to do testing under identical conditions on a number, say n of electric bulbs produced by the company. So, I pick up n bulbs at random and I conduct experiment on them and I observe their lifetimes. So, this leads to observing a realization small x, x1, x2, xn. So, realization I am always representing by small letters. So, I have a realization x which is x1, x2, xn of a random sample x1, x2, xn from the population. So, that realization comes after the experiment has been conducted. Here x1, x2, xn belongs to the sample space. My sample space in this case would be, because it is a lifetime, it could be collection of all those t1, t2, tn such that ti is greater than or equal to 0 and less than infinity. So, this chi is the sample space. Now, on the basis of realization x of the random sample x, the manager may want to answer several questions concerning unknown theta. So, let us see what kind of a questions one may have about the unknown mean lifetime theta. So, one is how to obtain a point estimate of theta, how to estimate theta, what would be the average lifetime of a typical bulb produced by the company. So, where I am interested in estimating the particular value of theta, this is an example of a point estimation problem. So, here I am estimating the unknown parameter. Now, this theta could be vector valued as well. In this example, it is taking values in R because it is a lifetime of a typical bulb produced by the company. Now, sometimes I may not be interested in knowing the exact value of theta, but I may be knowing in the interval in which theta belongs to with certain confidence. And that leads to how to obtain an appropriate interval in which the unknown theta lies with certain confidence. This is an example of confidence interval estimation problem. So, here also I am estimating theta, but I am estimating theta in the sense that I am saying that theta falls in certain interval with this much confidence or with this much probability. Now, that interval certainly has to be a random interval because there is a probability associated with it. Then there are other kind of problems where I may be interested in testing whether a given claim about the mean lifetime is correct or not. For example, somebody may make a claim that average lifetime of a typical bulb produced by a company is at least 1500 hours. That is a statement. There is a hypothesis which has to be tested based on the random sample. So, that falls under the third category, which is to verify the claim or hypothesis that theta belongs to theta naught. That means theta takes values in a given set where theta naught is subset of theta. This is an example of hypothesis testing problems. One can consider various variations of these problems, much more general problems than this. But these are three important statistical inference problems. So, first let us discuss about the point estimation problem. So, here I have a random vector x which is defined on a probability space P. So, it represents the characteristic of the population. It models the certain characteristic of the population. So, x has a distribution function f dot given theta. The functional form of f is known. However, theta is unknown. Theta takes value in capital theta, which we call as a parameter space. So, the basic situation is as follows. We observe random variables x1, x2, xn. This is before the experiment. After the experiment, I have a realization, so I have their observed values. So, we observe random variables x1, x2, xn from the population described by the distribution function f dot theta. Based on random sample x1, x2, xn, we seek an approximation or an estimate of this unknown quantity theta. So, let us look at this definition. So, let g theta, which may be a vector valued, be a function of unknown parameter theta. And suppose this is which we want to estimate. So, the quantity which we want to estimate is called the estimate. then g theta is called the estimate. So sometimes we may not be interested in directly estimating theta, but I may be interested in estimating some function of theta. For example, in certain situations, this theta may not be the mean. Theta plus 2 may be the mean. So I may be interested in estimating theta minus 2. Sorry, mean minus 2. So g theta becomes theta minus 2. So let capital lambda, which is collection of all those g theta such that theta belongs to capital theta, which is a subset of RQ, with the range of possible values of the estimate g theta. So I need an estimate of this. So I defined what do you mean by estimator of this. A statistics delta, which is delta x, is said to be an estimator of g theta. If delta maps the sample space, because sample space is the observed realization, so for each observed realization, it gives me a value which we take as an estimate of theta. So if delta maps the sample space chi into RQ, so that means for every sample realization, I get a value which we call as estimator. So that is the definition of an estimator. Now let me give, there is an estimator, then we can talk about estimator. Estimator is same as estimate. Estimator is a random variable because it is depending on the random variables x1, x2, xn. Now after the values of these x1, x2, xn have been observed after experimentation, so the estimator based on realization is called an estimate. So let x equal to x1, x2, xn be a sample realization of random vector x, and let delta is equal to delta x be an estimator of g theta. Then delta at the realization point is called an estimate of g theta. So this would be an estimate given by the statistician, because he has conducted the experiment and he says, look, this should be an estimate. So a small point over here in the form of this note to describe the difference between an estimator and estimate. Estimator is always a random variable because this you have to tell what estimator you are going to use before experimentation. Because estimator cannot be proposed after experimentation, because after experimentation you have seen the data. And after you have seen the data, there is a possibility that for proposing the estimator you may be biased and you may change your estimator as per your convenience. So a good statistician would always describe or propose the estimator before the experiment has been conducted, before he has seen what is going to be observed. So to cover more general situations in the definition of an estimator, we allow it to take assumed values outside lambda, which is the possible values of the estimate. This is just to have more generality in our model. The set of possible values of the estimate g theta, although it may look absurd, as we'll see in some of the examples. But this is just to have more general model. So what it basically implies is, in generality, my estimator may take values which may not be possible values of the estimate. Let us consider this example. So let x1, x2, xn be a random sample from a Poisson theta distribution. So Poisson distribution, I know that theta takes the value from 0 to infinity, the unknown parameter. In this case, I know that theta is also the mean of the distribution. And suppose estimate is theta itself. So I am interested in estimating the mean of a Poisson population. A reasonable estimate is the sample mean. So sample mean is an estimator of g theta. In the case of Poisson distribution, I know that mean is same as variance. So theta is also same as variance. So a reasonable estimate could be a sample variance also. So delta 2x is same as s square. Now note that both delta 1 and delta 2 here takes value in 0 to infinity. Now let us consider another example, another estimator which is of the type delta 3x, which is minus 1 to power x1 divided by x1. This is also an estimator of g theta. But it is absurd because it can take negative values. For example, if you observe x1 as 3, then it gives you delta 3x as minus 3 as an estimate of theta, which always takes positive values. So as per my definition, I consider this as an estimator, but this is certainly an absurd estimator. Now we'll discuss two commonly used approaches to estimate unknown parameter. First of them is the method of movements. and then we will discuss the method of maximum likelihoods.